Okay, in this example, we're going to be factoring out the monomial of 18x plus 30. Now, in order to do this, we need to figure out what the greatest common monomial is. And to do that, we're going to look for three different things. The first thing we're going to look for is the greatest number that goes into all the terms. So the biggest number that goes into 18 and 30, or the greatest common factor, would be, it looks like 6. I believe it is indeed 6. You can find that in a number of ways. One way is just to make a list of factors for each if you struggle with your multiplication tables. So the ways you can factor 18 are 1 and 18, 2 and 9, 3 and 6, and then for 30, the ways you can factor 30 are 1 and 30, 2 and 15, 3 times 10, 4 doesn't go into it, 5 does, 5 and 6, and any higher, and we're going to repeat. So those are all the possible ways you can factor both of the numbers, and the biggest one that occurs in both of those lists is 6. So that's how you can approach finding the common monomial if you struggle with multiplication. Just make yourself a list. And then after we have the number, the next thing we want to check to see is if there's a variable in all the terms. In this case, there is not. Only the first term has a variable, so we're not going to be pulling out any variables this time. And the third thing we want to check for is the leading coefficient negative. So in the term with the highest power, so that's that first term there, is that number negative? Well, in this example, it is positive, so we are going to pull out a positive monomial. So our greatest common monomial that we're going to be pulling out is 6. Now that we've determined what that monomial is, we will divide each term by 6. So 18 divided by 6 is 3. X is going to come along for the ride. And 30 divided by 6 is 5. So overall, the factored form, after pulling out the monomial, is 6 times, in parentheses, 3x plus 5. In this example, I'm going to be pulling out the common monomial, or factoring the common monomial. To do that, I'm going to look for three things. The first thing I'm going to look for is the greatest common factor between all the terms, number-wise. So between 6 and 4, the biggest number that goes into both 6 and 4 is 2. So 2 is the biggest number that goes into both. The next thing I want to check to see is if there's a variable in all the terms. In this time, we do have a variable in both terms. We have x in both terms. We want to take the lowest power of x that we see as part of our common monomial. In this case, we have an exponent of 2 on the first term and an exponent of the implied 1 on the second term. So the lowest exponent I see is x to the first. The third thing we want to check for is if the leading coefficient, or the term with the highest power, is negative. So the term with the highest exponent is this first term here, so the leading coefficient is negative 6. Since it is negative, we want to pull out a negative 2 and not a positive 2. Now that we have gone through and pulled apart the monomial, finding the greatest common monomial, or I guess with being negative is not the greatest, but we shall divide both terms by that common monomial of negative 2x, which will give us, in the first term, negative 6 divided by negative 2 is positive 3. When we divide the variable, we'll subtract the exponents, so x to the second, taking away x to the first, is going to give us x. And then the second term, we have 4x divided by negative 2x, so it will be negative 2. The x's will cancel out in that division, so this will be our expression. Remember that you can always check when you're factoring by redistributing. If we check, it's just distributing it through. So negative 2x times 3x is negative 6x squared, and negative 2x times negative 2 is positive 4x. So you can always double check. Factoring is the opposite of distribution, so you can always double check by redistributing to see if you get what you started with. Okay, now in this example, we're going to be factoring the expression 4x squared minus 25. In order to factor 4x squared minus 25, the first thing you always want to check for in factoring is to see if there's a common monomial. So looking in both terms, nothing goes into both 4 and 25 other than 1, and pulling out 1 won't really help here. There's not a variable in both terms, so there's no x that we can pull out, and the highest power is the x squared, and its coefficient is 4. So if we try to pull out a common monomial, there's nothing really helpful to pull out here. So the next step we want to check for in factoring is just to see if it's a common pattern. There's two common patterns that we can use right now: the a squared minus b squared pattern, and the a squared plus minus 2ab plus b squared pattern. Now, given the fact that this problem only has two terms, 1, 2, it's more likely going to be the first pattern if it is one. To check to see if it follows that first pattern, both terms must be perfect squares. So 4x squared has to be a perfect square. Well, is 4 a perfect square? Yes, 4 is 2 squared, so it is a perfect square. And x squared is a perfect square because we square x to get x squared. So I'm going to rewrite it like this. The second term, 25, is that a perfect square? Well, yes it is. 25 is 5 squared. So after writing it like this, I can tell that both terms are perfect squares. Therefore, it does follow the pattern, the a squared minus b squared pattern. And according to the pattern, a squared minus b squared is a plus b and a minus b. Remember that in this formula, a is what you square to get the original there, and b is what you square to get the 25 in the second term. So a is 2x and b is 5. So when we write out the factors of this, it's going to be 2x plus 5 and 2x minus 5. Okay, in this example, we're going to be factoring this expression using patterns. So anytime you're factoring, you should check for a common monomial, just in case. If I look at all three terms, there's no numbers that goes into all three terms, so no common monomial. The next thing we would check for is patterns. Since it specifically tells us to use a pattern to factor it, we are going to be using a pattern. Since this one has three terms, the pattern that we're going to need to use is the a squared plus minus ab, or not ab, 2ab plus b squared. And according to our pattern or our identity, its factors are a plus minus b squared. And you'll notice that the plus minus sign here is the same. So you keep the sign the same there. This sign is always going to be plus in order for this pattern to work. But first we need to make sure it follows that pattern. It should because it tells us to, but we should always double check. So the first term here must be a perfect square. Must match a squared. So is 4 a perfect square? Well, yes it is. 4 is 2 squared. And the x squared is also a perfect square. It is x squared. So the first term is indeed a perfect square. I'm going to check the last term now. So the last term has to be a perfect square. So 9 is indeed a perfect square. It's 3 squared. The middle term is a little bit harder to identify. It has to be twice a times b. And if we look at this, a is 3 and b is 2x. So is the middle term twice a times b? Well, 2 times 2 is 4, and then 4 times 3 is 12. So yes, the middle term does match up with what it should be based on what a squared and b squared happen to be. So since we have identified that it follows this pattern, according to the pattern, the factor is a keep that second sign, b, so in our case, 2x, keep the second sign, so our second sign is a minus, so 2x minus 3, and then that is in parentheses, being squared. So there is the factors. Okay, so in this example, we're going to be going through factoring this expression. We're going to be using the grouping method. So factoring the expression x squared plus 7x plus 12. As we go through, the first thing we want to check is to see if there's a common monomial in all the terms. And nothing goes into all three terms, so we're not going to have to worry about pulling out a common monomial for this example. The next thing we would check is to see if it's a pattern here, and it doesn't match the a squared minus b squared pattern, nor does it match the a squared plus minus 2ab plus b squared pattern. So it doesn't match either of the patterns, mostly because this last term is not a perfect square. So we're going to go through factoring by grouping, and the approach we're going to use is to start off by multiplying the first and last terms. If we multiply x squared and 12, we have 12x squared. The next thing we're going to do is find a combination of factors of 12 that will add up to be this middle term. So if you struggle with this, it helps to make a list of ways you can factor 12. 1 times 12, 2 times 6, 3 times 4. 5 times nothing works, and then if I go any higher, I'm going to get 6 again, and it's just going to repeat. So, yeah. Once you repeat, you found all the combinations. So now we just have to figure out the signs and which combination works. Because it multiplies to be a positive 12, I know both numbers have to be the same sign. And for both numbers with the same sign to add up to be a positive 7, they both have to be positive. So the combination that adds up to be positive 7 here is the 3x, or the 3 and the 4. Because they have to multiply to be, or add to be 7x, they both need an x, and which also matches the x squared up top. So this is the combination of factors that I want that will add up to be our middle term. Next thing I'll do for factoring by grouping is to break apart that middle term into the two factors that we just found. So we're going to separate it into x squared plus 3x plus 4x and then plus 12. So there we have it broken up. Now here's where the grouping part comes in handy, or comes into play. We'll focus on the first two terms and then the second two terms. We'll look at the common monomial between the first two terms to start with. So what's the common monomial between x squared and 3x? Well, it's just x. No number goes into both besides 1. So just x is needed because there's an x in both. And we'll divide both terms by x, giving me x to the first now plus 3. I'll do the same thing for the second grouping. What goes into both 4x and 12? Well, 4 goes into both. Because the leading coefficient there is a positive 4, we're going to be pulling out a positive 4. And no variable goes into both terms. So the common monomial is 4. And I'll divide both terms by 4. So 4x divided by 4 is 1x, which is just x. And 12 divided by 4 is 3. You should notice that x plus 3 and x plus 3 appears in both groupings. Well, now we're going to do the same thing. We're going to look at this as one giant expression and pull out that common x plus 3 between both terms, with this being the first term and this being the second term. If we pull out that x plus 3 from both terms, factoring out that common monomial between, or common binomial, I guess, between the two terms, we would have x left over in the first term and the plus 4 left over in the second term. Now there is a nice shortcut you can use, but the shortcut is only based on if there is no leading coefficient, or if the leading coefficient is 1. That's the only time you can use the shortcut. And that shortcut just involves, once you find the combination, that's actually going to be the factors in the parentheses at the end. But again, that only works if the leading coefficient is 1. Okay, in this example, we're going to be factoring the expression x squared minus 7x minus 30 by grouping. The first thing we would start to do is to check to see if there's a common monomial. There's not a common monomial in all three terms, so we can skip that. And the next thing we would check is to see if it's a pattern. But at the very least, 30 is not a perfect square, so it's not going to be a pattern. So we're going to go ahead and start factoring by grouping, multiplying the first and last terms, giving us negative 30 x squared. If you struggle with it, with finding factors, just make a list. 1 times what? Well, 1 times 30. 2 times what? 2 times 15. 3 times 10. 4 doesn't go into 30. 5 times 6. And then if I go any higher, it's just going to repeat. I know that one of the numbers has to be negative. Since it multiplies to be a negative number, one number will be negative, one number will be positive. We're looking for the combination that will add to be negative 7. So it looks like the combination I'm going to need is a negative 10 and positive 3. Now, I'm going to mention the shortcut here. Since there is no leading coefficient, I can jump straight to the factors once you find that combination. I know the combination is 3 and negative 10, so I can jump straight to the factors of x plus 3 and x minus 10. But that doesn't work if there is a leading coefficient that's not 1. So I'm just going to walk through the steps anyways here. Going down through the steps, we would need an x with both of these because they have to add up to 7x, the negative 7x. And then we would separate it into x squared plus 3x minus 10x minus 30. Then for the grouping, we group the first two together and the second two together. The common monomial in the first two is x, and we divide both terms by x. That would give us x in the first term and 3 in the second term. In the second grouping, the common monomial is, well, 10 goes into both numbers. Because the leading coefficient here is negative, we want to pull out negative 10. And let's see, I think that's it because there's no variable in both terms. So we'll divide both terms by negative 10, which is going to give us positive 1x, or just x, and positive 3. There we go. And then we also see that we have x plus 3 in both terms. If we pull that out, we'll have x plus 3 and the x minus 10. So as you can see, I got the same thing as what I did with the shortcut. But again, that shortcut only works if the leading coefficient is 1. And this is not the only strategy to factor polynomials or quadratics. So in this example, we're going to be factoring the expression 2x squared minus 5x minus 3. In order to factor this, I'm going to first check to see if there's a common monomial that goes into all three terms. And I know nothing goes into both 2 and 3 besides 1, and that's not actually helpful. There's not a variable in all three terms, and the leading coefficient isn't negative. So there's no common monomial. Then I would check to see if it's a pattern. Well, the last term there is not a perfect square, so it is not one of the two patterns we looked at. So, since it's neither a pattern or a common monomial, we shall just go ahead and do factoring by grouping. We're going to multiply first and last to get negative 6x squared. And again, if you struggle with breaking it apart, just make a list. 1 times 6 and 2 times 3 are the only combinations of factors that multiply to be 6. Because of the sign is negative, I know that 1's going to be positive and 1's going to be negative. We have to have the one that adds to be a negative 5. So the combination we're going to need is positive 1 and negative 6. Now the shortcut does not work here because a is not 1. The leading coefficient is not 1. So we cannot just do the shortcut. We won't get the correct answer in the long run. So we have to go through all the steps of factoring by grouping. So we're going to add the x to both terms and then break apart our expression. So we'll have 2x squared plus 1x minus 6x minus 3. We'll group the first two terms together. In the first two terms, it looks like the only common monomial I can pull out is just an x. So I will divide both terms by x, giving me 2x, and divide by x. And I do actually need to put a 1 here for a placeholder. Sometimes you do need 1s as monomials and stuff as placeholders. And then the second two terms, I guess the last two terms, common monomial here between 6 and 3 is 3. Leading coefficient here is negative, so we want to pull out negative 3. There's not a variable with both terms, so I'll divide both terms by negative 3, giving me 2x plus 1. You'll notice that these are the same, so we'll pull out the 2x plus 1 from both terms, which will leave us with x minus 3. And you'll notice that if I had tried to use the shortcut on this one, that would have led to x plus 1 and x minus 6. However, you'll notice that the factors are not the same and don't match up. So the shortcut only works if the leading coefficient is 1. It should not be used any other time. Okay, going through this example here, so we're factoring the expression 6x squared plus 7x minus 20. First check for common monomials, and there is not one because nothing goes into both 6 and 7. There's no x in all three terms, and the leading coefficient is not negative. The next thing I would look for is to see if it's a pattern. However, 6 is not a perfect square, so therefore it cannot be a pattern. So I'm just going to go ahead and do factoring by grouping, multiplying first and last. So 6x squared times negative 20 would be negative 120x squared. If you need to make a list of the ways you can factor negative 120, so 1 in 12, 2 in 60, 3 in 40, 4 in 30, 5 and 24, and I forgot my 0 with 120, 6 and 20, 7 doesn't go into 120, 8 times 15, 9, does 9 go into 120? Nope, 10 and 12, 11 does not go into 120, and if I go any higher, I'm going to get to 12, which is already on my list. So these are all the possible combinations of factors of 120. Now we just have to find the right one. So since it multiplies to be a negative, I know one of the numbers has to be positive, while the other number is going to be negative. We have to add to be a positive 7. So if I check my factors here, it looks like the combination I'm going to need is the 8 and 15, with the 8 being negative. So negative 8 times 15 is negative 120, and negative 8 plus 15 is positive 7. Both of them need an x. Now we're ready to start the grouping aspect of this. So we'll bring down the 6x squared and separate my 7x into negative 8x and positive 15x, and then bring down my minus 20. Remember, the shortcut doesn't work here because the leading coefficient is not 1. We'll next pull out the common monomial in both terms. So between 6 and 8, 2 goes into both, and there's also an x in both terms, so we're going to want to pull out 2x. And we'll divide both terms by 2x, giving me 3x minus 4. Then in the second grouping, what goes into 15 and 20? Well, 5 goes into 15 and 20. It's going to be a positive 5 because the leading coefficient is positive, and there's no x in both terms, so it's just going to be 5. Divide both terms by 5. that will give me 3x minus 4. Should once again notice that 3x minus 4 is the binomial in both of the groupings. So we'll pull out the 3x minus 4, which will leave us with in the first grouping, from the first grouping 2x, and from the second grouping plus 5. And there we have it. Okay, so in this example, we're going to be factoring the expression 6x squared minus 15x minus 36. The first thing we want to check when we're factoring is to see if there's a common monomial that goes into all three terms. And in this case, there is. It looks like 3 goes into 6, 15, and 36. So we're going to want to pull out that common monomial before we do anything else. So I'll divide each term by 3. Which will give me 2x squared minus 15x, 5x minus 12. Afterwards, I'm going to ignore the common monomial that I pulled out until the very end and continue to factor what's in the parentheses. So checking on what's in the parentheses, you should always double check and make sure you got the biggest monomial. There's nothing else that goes into all three numbers. And since 12 is not a perfect square, this is not going to be a pattern. So I'm going to go ahead and start grouping with just the stuff inside the parentheses. Multiplying first and last gives me 24x squared. And the ways I can factor 24 are 1 and 24, 2 and 12, 3 and 4, nope, 3 and 8, and 4 and 6. There we go. Since it multiplies to be a negative 24, I want one positive number and one negative. It has to be add to be negative 5. So the combination I'm going to want is with the 3 and the 8, with 8 being negative, 3 being positive. We need an x with each of them. Again, we're going to keep ignoring the 3 that we pulled out earlier. And we're going to go ahead and separate our terms so we can do grouping. So 2x squared plus 3x minus 8x minus 12. We'll look at the first two terms. See the common monomial? It looks like the common monomial here is just x this time. So we'll divide both terms by just x, which is going to give me 2x plus 3. In the second grouping, well, 4 goes into both 8 and 12. The leading coefficient is negative, so we're going to want negative 4. And there's no variable in both terms, so our monomial is just negative 4. So we'll divide by negative 4, give me 2x plus 3. Remember that these should be the same, so we can pull out that common binomial in both groupings, the 2x plus 3, which will leave us with x minus 4 left over from the two groupings. We're not quite done. Don't forget about that common monomial we pulled out way back in the beginning. We need to make sure to bring him down to finish the problem. Okay, in this example, we are going to be factoring the expression negative 15x squared minus 50x plus 40. In order to do that, the first thing we're going to do is check for a common monomial, so something that goes into all three terms. In this case, it looks like 5 goes into all three terms. No x's in all three terms. However, the leading coefficient is negative, so we actually want to pull out negative 5. So I'll divide all three terms by negative 5. If I do that, negative 15 divided by negative 5 is positive 3x squared. Negative 50 divided by negative 5 is positive 10x. And 40 divided by negative 5 is negative 8. Afterwards, we would check to see if there's a common or one of the patterns. However, the first term, 3x squared, 3 is not a perfect squared. So it's not a pattern. So we're going to multiply first and last so we can start grouping, which is going to give me negative 24x squared. And I'll quickly make a list of the ways we factor 24, 2 and 12, 3 and 8, and 4 and 6. We are looking for the combination that multiplies to be a negative 24. So I know one number is positive, one number is negative, but adds to be a positive 10. Remember, when we have a monomial, we're going to ignore it until we finish the grouping. So the combination that we're going to want is going to be with the 2 and the 15. We are going to need the 2 to be negative and the 12 to be positive. And I said 2 and 15. I meant 2 and 12. We need an x with both of them. So we're going to keep going, and we shall separate our terms to the 3x squared, and then our minus 2x. Remember, since our leading coefficient is 3 here, we cannot use the shortcut. 12x, and then minus 8. Ignoring my monomial, the negative 5 until the end here. So looking at the first two terms, grouping-wise, I think x just goes into both. So we'll divide both terms by x, which will give me 3x minus 2. And in the second two terms, let's see what goes into both. It looks like 4, positive 4, because the leading coefficient is positive 12. And there's no x in both terms, so we'll just be dividing by 4, which will give me 3x minus 2. Once again, in both terms, the binomial should be the same, or in both groupings, the binomial should be the same. So we'll pull that out, which will leave me in the first grouping, x, and in the second grouping, plus 4. But remember, don't forget to bring down the common monomial that we pulled out at the beginning. So negative 5. And there we go. Okay, in this example, we're going to be examining the connection between roots and factors. Roots, remember, are x-intercepts. So we have this graph here, and you can clearly see the x-intercepts, which are the roots, on the graph. So right here we see one of the roots is x equals negative 1. The other root is x equals 3. As far as the factors go, for x squared minus 2x minus 3, if I try to factor this, there is no common monomial, and it's not a pattern. So I can multiply first and last here. For grouping, give me negative 3x squared. The only way we can factor 3 is 1 and 3. Since we have to add it to be negative 2, we're going to want the combination of 1 and negative 3. Since the leading coefficient is 1, we're going to jump straight to the end with the shortcut here. So we're going to have x plus 1 and x minus 3. So if you look closely at the factors and the roots, one of the roots is negative 1, while one of the factors is x plus 1. The root and the factor is opposite. And same thing with the other root and the other factor. Essentially, the roots are gotten by taking each of our factors and setting them equal to 0. That's where it's coming from, or the connection between the two. Which leads us to one of my favorite properties in algebra, the zero product property, which just says that if we have two numbers, n and m, multiplied together to equal 0, then either n equals 0 or m equals 0. Okay, so we're going to solve this equation. Now, in order to solve a quadratic equation, you can do it in several ways, but the way we're going to be doing it here is by factoring. So in order to do it by factoring, we have to make sure it's equal to 0 first. So we have it currently equal to 7, so we're going to move everything to one side by subtracting 7 from both sides of the equation. That's going to give me 4x squared plus 12x minus 7 equals 0. Now the next step I'm going to do is to just factor this quadratic on the left side. So there's not a common monomial in all three terms, and it's not a pattern because 7 is not a perfect square. So I'm going to multiply first and last, giving me negative 28x squared. The ways I can factor 28 are 1 and 28, 2 and 14, 3 doesn't go into it, but 4 and 7 does. I think that's the last combination. Since it multiplies to be a negative, I know one of the numbers is positive and one of them is negative, but we have to add it to be a positive 12. So it looks like the numbers we're going to want are the 2 and the 14, with the 2 being negative. And of course, adding an x to each. With that, we'll go ahead and start setting it up for grouping. I'm going to ignore the equals 0 while I do the factoring part. So 4x squared. Then we're going to separate the 12x into negative 2x and positive 14x. And then minus 7. Again, ignoring the 0 until I'm done with factoring. In the first group, it looks like 2 and also x goes into both terms. So I'll divide both terms by 2x. Giving me 2x minus 1. 2 divided by 2 is 1, and x divided by x cancels out. I do need that 1 as a placeholder. In the second grouping, what goes into both terms? Well, it looks like 7 goes into both 14 and 7. Leading coefficient is positive, so plus 7, and there's no variable in both, so just 7. So 14 divided by 7 is 2, so 2x, and then negative 7 divided by 7 is negative 1. So there we go. Again, we need that placeholder of the 1 there. And once again, we should see the same thing in both groupings, the 2x minus 1. If I pull that out, that will give me 2x plus 7 left over. And now, if we were just factoring, we would be done. But this is a solve question. So we're not quite done. Don't forget to bring down the equals 0. Now, from here, this is where the zero product property comes into play. The zero product property says if we have two things multiplied together to equal 0, then one of those two things equals 0. So we just set them both equal to 0. They can't both be equal to 0 at the same time, but those are both possible solutions. So here we have two different binomials multiplied together to equal 0. So we'll set 2x minus 1 equals 0. And we'll also set 2x plus 7 equal to 0. And then we'll just solve each of those equations. So I'll add 1, get 2x equals 1, and divide by 2. So x equals 1/2 is one of the answers. And then I will subtract 7, get 2x equals negative 7, and divide by 2. To get x equals negative 7/2 as the other answer. And there we go. Okay, in this example, Spider-Man is jumping down from a 32-foot high platform. His height in feet is modeled by the equation f of x equals negative 16x squared plus 16x plus 32, where x is time in seconds. When will we reach the ground? So we have little Spider-Man up here, and he's jumping down, woo, going until he hits the ground. When you think about this problem, he is 32 feet high to start with, 32 feet above the ground. Well, his equation models the height, and we are looking for when he reaches this point on the ground. Since the equation models height, we need to think about how high off the ground is the ground. Well, the answer to that, 0 feet. When he hits the ground, he will be 0 feet off the ground. So what we're asked about in this equation is how long will it take for his height to reach 0? In other words, when the equation representing height is equal to 0. That's what we're looking for. So now that we have it set up, we just have to go through and solve this. So if we start solving, we're going to try solving by factoring. So looking at all three terms, is there a common monomial? Yes, it looks like 16 will go into all three terms. Negative 16 because the leading coefficient is negative. So I will divide all three terms by negative 16. Which will give me positive 1x squared, or just x squared, minus 1x, or just x, and minus 2 equal to 0. I'll continue with factoring, ignoring the 16, and doing grouping, multiplying first and last, giving me negative 2x squared. The ways I can factor negative 2 are 1 and 2. And the combination I need to add up to be the middle term, which is negative 1, is going to be positive 1 and negative 2. Since the leading coefficient is 1, we're going to go ahead and use the shortcut, jumping straight to the factors of x plus 1 and x minus 2. Don't forget to bring down the monomial of 16. And the equals 0. Now that we have this, we can apply the zero product property. We have a bunch of things multiplied together to equal 0. So one of those things will be set equal to 0. And by one of them, I mean each one. So 16 will be set equal to 0. X plus 1 will be set equal to 0. And x minus 2 will be set equal to 0. We would just solve each of those equations. The first equation here doesn't have an x, so we can't actually get a solution out of it. The answer is not no solution because we still have other parts of the expression to solve. The middle one will subtract 1 from both sides, giving us negative 1, and the last one will add 2 to both sides, giving us x equals 2. Now, this is a word problem, so it's a little bit different from the other ones we've looked at. And word problems involve real-life situations. X is representing time in seconds. If we think about it, negative 1 second would mean 1 second before he jumps. So what this first answer would be saying is that 1 second before he jumps off the platform, he reaches the ground. Most of the time in real-life situations, negative solutions aren't going to make sense. So the answer we actually want is 2 seconds. 2 seconds after he jumps is when he will hit the ground. Okay, in this example, we're going to be graphing this function using the roots and the vertex. So, with that, we're going to start by finding the roots, which are zeros or x-intercepts. And the key thing about zeros, roots, and x-intercepts is they're all solutions when the equation is set equal to 0. So we'll just take our equation, which is negative 2 times x plus 2 times x minus 4, and set it equal to 0. Now, if this one wasn't factored, we would have to factor it before actually starting this. But since it's already factored, we're going to go ahead and just apply zero product property. Negative 2 equals 0, x plus 2 equals 0, and x minus 4 equals 0. And just solve each of those. Negative 2 cannot equal 0, so we'll subtract 2, giving us x equals negative 2, and add 4, giving us x equals 4 for the last solution. So these are roots, zeros, or x-intercepts. Since we're graphing, I'm going to go ahead and plot those points. So negative 2 is one of my x-intercepts, and 4 is the other x-intercept. There we go. Now we are just going to go ahead and find the vertex. Now for the vertex, it's a little bit different when we are using factored form. So when we had it in vertex form, we could use transformations. In standard form, we had a formula to find the axis of symmetry, which we then plugged back in to find the y value for the vertex. But in factored form, we have to approach it a different way. We could always rewrite it in standard form, but there's a way to do it here. Since we know the roots and we know the fact that a quadratic is symmetric, these 2 points are at the same height, which means halfway between those 2 points should be the location of the axis of symmetry. Because again, quadratics are symmetric. So to find the axis of symmetry, we're simply just going to add the 2 points together, the 2 x values together, and divide by 2. So if I take my 2 x values, take the average of the x-intercepts, my 4 plus my negative 2, and divide it by 2 for the average, or halfway between, we'll have 2 over 2, which is 1. So x equals 1 should be the axis of symmetry. It's just halfway between the two x-intercepts. Now that we have that, the next thing we'll go about doing is to try to find the y value for the vertex, because vertex is an ordered pair, x comma y. We now have the x value of 1. To find the y value, we just plug x back into the equation. So we'll replace x in my equation with 1. So we'll have 1 plus 2 and 1 minus 4. Negative 2 comes down, 1 plus 1 is 2, and 1 minus 4 is negative 3. Negative 2 times 2 is negative 4, and then negative 4 times negative 3 is positive 12. So my y value for the vertex is 12, making the vertex the point 1, 12. Now we just have to try to draw the U-shaped graph in as best we can. So let's give it a go. Yeah, probably not the best I've ever done, but not too bad. There we go. Okay, so in this example, we're going to be writing the equation for a parabola, which is the equation of a quadratic function, with x-intercepts at negative 2, 0, and 1, 0, which passes through the point negative 3, 20. Since we're given the x-intercepts are connected to factors. That's the connection. So if we're given x-intercepts, roots, or zeros, we want to write the equation in factored form first. In order to write it in factored form, the first thing I'm going to look at is just the general format, which is here off to the side now, a times x minus the root 1 times x minus root 2. And to go about doing this, I'm just going to kind of work the zero product property backwards, starting with my two roots of negative 2 and 1. Well, working the zero product property backwards means that we need these both set equal to 0, plus 2 on both sides. So x plus 2 equals 0, and subtract 1, x minus 1 equals 0. So my two factors are going to be the x plus 2 and x minus 1. Now I could have also just jumped straight to it because I know the roots and the factors are opposite signs. But if you work like this, you can deal with the fractions as you go through them, through the process. So I don't like dealing with fractions in this equation, but I know some people will. And just working backwards will allow you to kind of get rid of them as you go. But we're not quite done here. We still need to figure out what the possible value for a is, if there is even one. And that's where this other ordered pair comes in handy. We have the ordered pair negative 3, 20. Negative 3 is the x value, 20 is the y value, so we'll just plug those in. This way we'll be able to solve for a. So negative 3 plus 2 and negative 3 minus 1. Going through here, I'll just go ahead and simplify each of the parentheses. Negative 3 plus 2 is negative 1. Negative 3 minus 1 is negative 4. And we have negative 1 times negative 4, which is positive 4a, equals 20. Nice, easy one-step equation, dividing by 4 on both sides. So a will be 5. But remember, finding this value for a is not actually the goal of the question. The goal is to write the equation. So the actual answer of writing the equation is y equals 5 times x plus 2 times x minus 1. If you requested the equation in standard form, it would be at this point you would just distribute everything out and it would be done. But since we're not requested a form, we'll leave it in factored form and say this is our final answer. Okay, so in this example, we're going to identify intervals on which the function y equals x squared plus 2x minus 3 is positive and which intervals it is negative. So the first thing we need to do for positive and negative, just as a reminder, is we need to figure out where the x-intercepts were. Now we could always graph this and stuff, but the point of this is to actually approach this without actually using the graph. So I'm going to start by figuring out where those x-intercepts are. And in order to do that, I'm going to resort to our favorite thing, factoring. So we're going to set the equation equal to 0 because x-intercepts are solutions when the equation equals 0. We'll go ahead and multiply first and last so we can factor. There is no common monomial and no pattern for this one, so I'm kind of jumping straight to this point. So the only way I can factor 3 is 1 and 3. The combination we needs to multiply to be a negative 3 and add to be a positive 2. So we are going to want a negative 1 and positive 3. Since the leading coefficient is 1, I can use the shortcut, which means our factors will be x minus 1 and x plus 3. Now I'll apply the zero product property, setting each factor equal to 0, and then solving each equation. So I will add 1 to both sides, giving me x equals 1, and subtract 3 from both sides, giving me x equals negative 3. So at this point, I can kind of get this little picture that I have this graph with x-intercepts at 1 and at negative 3. Now, our goal here is to do intervals of positive and negative, so we just need to figure out a little bit more to do that. Now, there's two ways I can actually approach this. Thinking back to earlier, this separates our graph into 3 separate intervals. The first interval being negative infinity until negative 3, negative 3 to 1, and 1 to infinity. Now, method 1 is purely numerical, purely algebraic, not looking or thinking about a graph at all. And that's just picking some test points and seeing whether it's positive or negative in each of those intervals. So if I go and plug in a number from the first interval, so on the first interval, an x value might be x equals negative 5. That's on the first interval. And x equals 0 is on the second interval. And x equals 7 is on the last interval. If I plug that into my equation, whether it's the factored version or the original version, I can figure out whether it's positive or negative. I'm going to plug it into the factored version just because it's a little easier to do mental math with. So negative 5 minus 1 times negative 5 plus 3. If I do that, we'll have negative 6 times negative 2, and a negative times a negative is a positive number, positive 6. All I really care about is whether it's positive or negative. So I know that the first interval is positive. From negative 3 to 1, my test number was 0, so if I try plugging 0 in, 0 minus 1 times 0 plus 3. 0 minus 1 is negative 1. 0 plus 3 is 3. Negative times a positive is a negative. Negative 3. All I really care about, though, is that it's negative. In the third interval, my test number was 7 that I chose, and I could have chose any number. There's no real reason why I chose that specific number on the interval, so between 1 and infinity. So 7 minus 1 and 7 plus 3. If I try this, 7 minus 1 is 6. 7 plus 3 is 10. 6 times 10 is 60, which is a positive number. So the last one is also positive. So there is method number 1 for doing this. Method number 2 is just using some features of the graph. So just quickly with the graph. 1, 2, 3, rough sketching the graph again. We have our intercepts at there and there, breaking my graph into the 3 sections again. We have my sections are from negative infinity to negative 3, from negative 3 to 1, and then from 1 to infinity. Well, the easiest way to do this, even easier than the numerical way for the first method, over here for method 2 is just to look at the leading coefficient. If the leading coefficient is positive, then it's a u up. If it's a negative leading coefficient, then it's a u down. In this case, we have a positive leading coefficient, so I have to have a u that goes upwards, that goes through both these points. The only way I'm going to do that is like this. Now, this part here might be longer or shorter, and these might be steeper or less steep, but this is the only way I could actually draw it so that the u goes through both those points. If I have the u too far up, it's not going to go through the points, or too far down and it misses. Yeah, this is the only way I can actually draw the u so that it goes through both points. And from this you can tell that the first area is positive, the second area is negative, and the third region is also positive. No matter which way you do it, you get the same answer. One way is kind of more of a graphical, and one way is more of an analytical. But both ways give you the same thing. Okay, in this example, we're going to be just factoring out the monomial. So with this one, we want to look for the common monomial, so that includes the number that goes into both terms. In this case, 5 goes into both terms. We'll also check for the variable, if there's a variable in all the terms. There is an x in all the terms. And we want to take the lowest exponent with x. So in this case, it's going to be 3. And the leading coefficient is 5. It is positive, so we're going to be pulling out positive 5x to the third as our common monomial. Then once we have that, we'll divide both terms by 5x to the third. So 5 divided by 5 is 1, and x to the fourth divided by x to the third. Just subtract their exponents. It's one of the exponent properties, which will give us 1x to the first, and both those 1s are implied ones, so we don't need to write them. Next, we have the negative 30 divided by 5 is negative 6. And then x to the third divided by x to the third. Subtracting the exponents are 0 and canceling out. If we had nothing left at all, we would need a 1 as a placeholder, but we do have the 6 there. And there we have it. Normally we would try to factor farther, but since this is linear, a linear factor, we can't really go any farther. Okay, in this example, we're going to be factoring this expression. Since we're sticking right now with a quadratic unit, we will be factoring it in any sort of quadratic way. So we'll check for a monomial, and there is not a common monomial here. So we would look for a pattern, and it looks like it's not a pattern because that first term at the very least is not a perfect square. So I'll go ahead and start factoring by grouping, multiplying the first and last terms, hoping grouping works, and it should given our current unit that we're in. Okay, if I multiply first and last, I get 144 x squared y squared, negative 144 x squared y squared. We need the combination of factors that will add up to be the middle term, which is 7. If you have trouble, just make a list of factors. 1 and 144, 2 and 72, 3 and 48, 4 and 36. 5 doesn't go into 144. 6 and 24, obviously. 7 doesn't go into 144. 8 does. 8 times 18. 8 times 18. 9 goes into 144. Let's see. 9 times 16. 10. 10 does not, 11 doesn't, and 12 times 12. Ooh, there's all the combinations. We're looking for the one that adds to be negative 7, given the fact that 1's going to be a positive and 1's going to be a negative. So I think the one we need is this. I believe I said negative 7, but I mean a positive 7 there. So the combination we need is a negative 9 and a positive 16. Because the middle term has xy as its variable, we're going to need xy in both of them. And if you look, negative 9xy times 16xy should add up or multiply to be negative 144 x squared y squared, both variables being squared. So we have the right combination. Now we'll continue with the grouping process, breaking apart that middle term. So we'll have 6x squared minus 9xy plus 16xy, and then minus 24y squared. Now, part of this when you're doing the grouping is to factor out the common monomial. When we do this, because sometimes we want to pull out negative and sometimes we don't, we want to make sure we focus on the same variable when we're deciding that. Since my first term has x in it, I'm going to focus on the power of x to determine whether I pull out a negative or not. Technically, all of these terms have the same degree. With that being said, the first two terms, the common monomial between the two is apparently 3 goes into both 6 and 9, and there's an x in both terms. Since the first term, the term with the higher exponent of x, is positive, we'll pull out positive 3x. That's going to give me 2x minus, divided by 3, so 3y. In the second grouping, what goes into both 16 and 24? I believe it is 8. Because the higher power of x here is a positive 16, we're going to be pulling out a positive 8. And we also have a y in both, so we're going to pull out positive 8y. So we'll divide both terms by 8y, which is going to give us 2x minus 3y. And just like normal, you should see that these are the same binomial expression. So we'll pull out that from both groups, which will leave us from the first group 3x, and from the second group plus 8y. And there we have it. Okay, in this example, we're going to be factoring x to the fourth minus 14x squared plus 45 completely. So as we go through and do this, since the current unit we're looking at is a quadratic unit, we're going to be focusing on using the quadratic process of factoring. So checking for a monomial, which there isn't one. Checking for a pattern, there isn't one because 45 is not a perfect square. So we'll go ahead and start off by trying factoring by grouping. And it should work during this unit. So x to the fourth times 45. Later on, if we're trying to factor, we might have to use long division. But right now, x to the fourth times 45 gives us 45x to the fourth. We'll make a list of factors. 1 and 45. You only really need to do this if you're struggling finding the combination. 2 doesn't work, but 3 and 15. 4 doesn't work, 5 and 9, and that should be the only combinations. Because it multiplies to be a positive, I know the signs are the same. In order to add up to be a negative, though, they're both going to have to be negative. So, negative 5 and negative 9 is the combination I want. We also want to give an x to both of them. Not an x to both of them, but an x squared to both of them, because the middle term is x squared. We'll go ahead and continue with grouping. Since the leading coefficient is 1, we can actually skip a lot of the grouping steps and go straight to the actual thing. And I would normally do that if it wasn't one of these problems, but I just want to walk through the process with the x squareds. So if I go through it, breaking it apart, x to the fourth minus 5x squared minus 9x squared plus 45. If I look at the first two terms here, the common monomial here is going to be x. X is in both, and the lowest exponent of x I see is x squared. So I'm actually going to have to pull out x squared from both terms, which will give me x squared in the first, just subtracting the exponents, minus 5, and the x squareds will cancel out from the second grouping. Then from the next two terms, common monomial will be 9 in both terms. Leading coefficient is negative, so we want to pull out negative 9 from both terms. which is going to give us a positive x squared and a negative 5. From here, we'll continue to factor it. This is the same in both terms as normal. If it was not, we either made a mistake or factoring by grouping just doesn't work, and we would have to try a different strategy, which we'll talk about later in the year. So we have x squared minus 5 and x squared minus 9 as our two factors. However, with this one, we might actually be able to go farther. Because they're both quadratics, we want to continue to try to factor. The first one here, x squared minus 5, because there's only two terms, the only way we're going to be able to factor it is if it's that pattern where both terms are perfect squares. 5 is not a perfect square, so we can't actually do anything with this first one. However, x squared minus 9, both terms are indeed perfect squares. So that follows the a squared minus b squared pattern, which says its factors are a plus b and a minus b. So x squared is really just x squared, and 9 is 3 squared. So it follows this pattern where a is x and b is 3. So x plus 3 and x minus 3 are the factors of x squared minus 9. And my x squared minus 5 just comes along for the ride, making this the completely factored version.